Welcome back. If you're tracking the cutting edge of unified AI, you know the holy grail right now is getting a single multimodal model that can both really understand an image, I2T, and generate a great image from text, T2I. Today, we're doing a deep dive into Manzano, a simple and scalable unified multimodal model. This is Apple's pretty impressive take on this challenge.
Yeah, it's a really foundational piece of work, I think. For the engineers and researchers listening, maybe looking for that immediate takeaway, like the 1-minute summary for your stand-up, the Manzano team essentially figured out how to handle that performance trade-off. You know, the one that's always plagued these unified MLLMs? They tackled it right at the tokenization bottleneck.
Okay, so tell us what exactly is that bottleneck and how did they break through it?
Right. So the problem, it's technical, but it's absolutely critical. Traditionally, these unified models, they sacrifice visual understanding performance, especially on tasks needing fine detail as soon as you add generation capabilities. And this conflict, it pops up because understanding tasks, they really thrive on these rich, continuous features. But the autoregressive generation process, that needs discrete tokens, and often those tokens come from a kind of lossy separate source.
Gotcha. And Manzano's core innovation here, the thing that resolves this deep-seated conflict.
They brought in this thing called a hybrid image tokenizer. And the real breakthrough, I think, is its structural simplicity. You have a single shared fission transformer encoder.
Yeah, okay.
And that feeds into two lightweight adapters. One gives you continuous features for understanding, the I2T part. The other gives discrete tokens for generation, T2I. And because both token types start from this homogeneous source, they naturally share the same high-level meaning, the same semantics. This alignment, it completely changes things for the unified LLM decoder downstream. It dramatically cuts down on that internal task conflict.
Wow, okay. That structural unity, that shared source, that sounds like a huge deal. And the results?
Oh, the results back it up. Manzano gets state-of-the-art results among the unified models out there. It performs really competitively, even with models built just for one task, these specialist models. And crucially, like you hinted, it absolutely shines on benchmarks that need fine visual detail. Think text-rich stuff like DocVQA and OCR bench.
Right, and they showed it scales too.
That's right. That was a key goal. The system proves it's scalable. They took the LLM backbone from like 300 million up to 30 billion parameters.
Yeah.
And saw these robust monotonic performance gains across both understanding and generation tasks. It shows the design really holds up under pressure.
That insight, the homogeneity, the single source for tokens, yeah, that feels like exactly what the community's been wrestling with. Okay, let's unpack that core tension a bit more first. Why is unification usually so bad for understanding tasks?
Well, the difficulty, it really lies in the, let's say, the fundamental nature of the tasks themselves. When you want the LLM to generate an image, the T2I part, it basically needs to predict the next token in a sequence, just like it does when generating text. And to do that well in an autoregressive model, you kind of have to use these discrete, quantifiable image codes. Think like indices from a VQVAE codebook.
Right. But the second you quantize or discretize that visual input, you inevitably lose some of that fine-grained detail. The very detail you need for tasks like reading a chart accurately or pulling text out of a document, the I2T stuff, those need the dense, continuous embeddings.
Precisely. And previous attempts, they often tried using maybe a dual encoder strategy. So separate encoders, one for continuous features, one for discrete codes. But this forces the LLM to try and reconcile tokens that are just different types, right? They're derived from completely different computational paths, different semantic spaces almost. It's kind of like asking the LLM to learn two different visual languages at the same time for the same basic concept. That's the conflict Manzano was really built to get rid of.
Okay, so if the design goal was simplicity and scalability, the Manzano architecture needed to be minimalist but still really powerful. Can you walk us through the three main components?
Yeah, sure. So you've got the hybrid vision tokenizer, which is, the star here. Then there's the unified LLM decoder, which runs the main autoregressive show. And finally, a separate diffusion image decoder, which handles the actual pixel rendering at the end. But the key design principle, it always comes back to this. Both the continuous features for understanding and the discrete tokens for generation are processed through the same vision transformer backbone first. This guarantees they live in that shared, unified semantic space before they even hit the LLM.
Okay, let's zero in on that secret sauce then, the hybrid vision tokenizer. How exactly do they get both types of tokens from that single source without immediately, losing all the important detail?
Okay, so it starts with a standard vision transformer, a VIT. Pretty standard stuff there. This then feeds into two parallel adapters. Now, for the continuous channel, the one focused on understanding, they first use something called a spatial-to-channel STC layer. You can think of the STC layer as like a smart compression step. It reduces the spatial size of the token grid maybe from 42 by 42 down to 14 by 14 tokens, for example. And then it uses a simple MLP, a projection layer, to get those rich, continuous features into the right dimension for the LLM.
Okay, makes sense. And for the generation side, the discrete channel.
It actually follows the same initial STC compression step. So that maintains the structural consistency, which is neat. But before the final MLP projection, it applies finite scalar quantization, FSQ. And they specifically chose FSQ because it's computationally pretty simple and it scales really well, which is super important when you're managing a very large code book, like 64,000 codes in this case. And that's how the LLM gets the discrete indices it needs to predict during text-to-image generation.
Okay, so at inference time, if you want the model to do some high-fidelity reasoning, the LLM taps into that continuous path. But if you want it to generate a new image, the LLM predicts a sequence from that set of 64K discrete tokens. Sounds elegant in theory, but doesn't forcing both types of features through the same, limited vision backbone inevitably compromise the quality of those continuous features somehow? What was the trade-off?
Yeah, that's the absolute critical question, isn't it? The training process, and especially the ablation studies they ran later, they suggest the trade-off is actually minimal. And that seems to be because of that early alignment they forced during training. And speaking of components, that final piece, the image decoder, it's actually decoupled from this whole process. It's trained completely separately. They use a Ditier architecture, which is a pretty sophisticated type of diffusion transformer, and it operates in the latent domain, not directly on pixels initially. This separation means the LLM can focus purely on the semantic prediction part, understanding or generating the sequence of tokens, while the decoder handles the heavy lifting of high-resolution rendering. It supports outputs up to 2048 pixels, which is quite good.
Right. Let's talk about that unified training regime then. Aligning these two parallel streams, especially getting the continuous and discrete representations to play nice, that must have involved a pretty careful recipe.
Yeah, it was definitely structured, a three-stage approach. The first stage is what they call Tokenizer pre-training. So they pre-trained the VIT using CLFP, standard practice. Then they attached it to a small LLM, just 300 million parameters. Now, the crucial step here is that they randomly sampled outputs from either the continuous or the discrete adapter to train that small LLM. This early, deliberate cross-training forces those two feature streams into a common semantic space before you even start the main training. It's like getting them on the same page early on.
Okay, that sounds like the key to actually solving that homogeneity problem you mentioned. You're pre-aligning the two token sets from the get-go. So what happens in the main event, the unified LLM training stage?
Right, so at this stage, they freeze the hybrid tokenizer. That locks in the 64,000 discrete image tokens as part of the LLM's vocabulary. Then the training objective is joint. The continuous features are used as input for the understanding tasks, the I2T stuff, using a standard text loss. And the discrete tokens serve as the targets for the generation tasks, T2I, using an image loss. And they found the optimal balance required a specific weight ratio. The text loss to image loss was set at 1 to 0.5.
Huh. Why that specific 1 to 0.5 ratio? Did they find that, if they weighted the generation loss too much, it started hurting the understanding performance again?
That seems to be the implication, yeah. They needed to make sure that the discrete path, which, remember, is only really used for generation, got enough attention, enough signal to accurately predict that long sequence of 64K tokens. But without overwhelming or degrading the continuous path that's driving all that strong reasoning performance. That 1 to 0.5 ratio was likely the sweet spot they found experimentally. It's where the LLM could learn to predict high-quality discrete tokens for making images, while still getting maximum fidelity from the continuous features when it needed to understand images.
Okay. And the proof is in the pudding, right?
Yeah.
The Abolation Study should show if this homogenization strategy actually cut down the conflict. What did they find comparing their hybrid approach against the baselines?
Yeah, the findings were a really strong validation of their whole design philosophy. First, they compared the hybrid tokenizer against a baseline that only used discrete tokens, a pure discrete setup. And, as you'd probably expect, the pure discrete model showed a massive drop in understanding performance, especially on things like text-rich VQA. Just too much detail lost in the quantization.
Okay, that outcome makes sense, but the next comparison is maybe more telling. Did the hybrid tokenizer actually do better than just using two separate specialized encoders, like the dual encoder approach you mentioned?
Yes, it did. The dual encoder baseline, which used dedicated encoders but kept them separate, still consistently underperformed the Manzano hybrid tokenizer. And this really underscores their core idea. The conflict wasn't just about the type of token, continuous versus discrete. It was more about the LLM being forced to juggle tokens coming from these heterogeneous sources, these different pathways. It's that shared semantic origin of Manzano's tokens from the single VIT that really seems to have resolved the issue.
Right. And the ultimate test is scaling, which you said was a core goal. So what happened when they really pushed it? Took the LLM decoder from that small 300 ML model way up to 30 billion parameters.
The scaling results are incredibly robust. They saw monotonic improvements, pretty much a straight line going up across all the benchmark categories: general understanding, knowledge-based tasks, generation quality. We saw some really massive practical jumps too. For example, those text-rich tasks. They improved by over 10 points, just going from the 300 million to the 3 billion parameter scale. So scaling the LLM clearly improved its core reasoning ability, and that directly translated into better image analysis.
And qualitatively, you could see the scaling effect in the generated images too, right? Especially in complex scenarios.
Exactly. Scaling up the LLM size directly improved the semantic complexity it could handle in generated images. For instance, the bigger LLM got much better at rendering complex text accurately within an image based on the prompt, or seamlessly integrating multiple kind of nuanced concepts together. Like maybe you need a picture with a specific type of church and a railroad crossing and a particular sign all in one coherent scene. The larger LLM was just better at managing that high-level world knowledge and semantic integration.
What about scaling the other part, the separate image decoder? Did making that component bigger have any knock-on effects on the understanding performance?
This was actually fascinating. When they scaled the image decoder from about 0.9 billion up to 3.5 billion parameters, it did not negatively impact the understanding performance at all, which really validates the stability of keeping that decoder decoupled. But in human evaluations, the larger decoder substantially improved the structural integrity of the generated images. People rated them as much more coherent, leading to almost a 10-point score increase in that aspect.
But the automated metrics didn't quite show that same leap, did they?
They didn't, know. The standard automated metrics, things like GenEval and DPG, they kind of showed performance saturation. They plateaued, which suggests they might just not be sensitive enough to capture these more nuanced improvements in structure, or maybe world knowledge consistency that the larger LLM and decoder were enabling. Although interestingly, the WISE benchmark, which specifically tries to evaluate world knowledge grounding in images, did continue to show some modest gains with scaling.
That observation about the automated metrics hitting a ceiling, that feels like a really critical point for where research needs to go next. But first, looking at the competition, how does Manzano 30B stack up against other big models, including the specialists? Where does it land overall?
Well, it's certainly a dominant unified model. The Manzano 30B version ranks first on several complex reasoning benchmarks like ScienceQA, MMU, and MathVista when you compare it within its size class. But perhaps most importantly for proving its unified credentials, it actually achieves the best performance among all comparable models, whether they're unified or specialist, on 4 out of the 5 major text-rich benchmarks. That includes things like ChartQA and DocVQA. So it pretty decisively shows that unification done this way doesn't mean you have to sacrifice that detailed visual accuracy needed for many real-world applications.
And beyond just the standard benchmarks like VQA and T2I, this architecture seems naturally suited for other high-demand applications, like complex image editing. How does Manzano use its hybrid design for that?
Yeah, image editing becomes a pretty natural extension of this unified setup. Manzano does conditional image editing by feeding the reference image, the image you want to edit, into 2 distinct paths at the same time. The LLM gets the image so it can understand the instruction, the semantic change the user wants, and maintain the overall coherence of the scene.
And the decoder also gets the image, presumably to maintain the pixel-level fidelity and structure.
Exactly right. The diffusion decoder needs that reference image to know where and how to apply the instructed change to the existing pixels without messing everything else up. It's this coordination between the LLM figuring out the what and the decoder handling the how at the pixel level that enables some really versatile and complex editing.
Can you give an example of that complexity, especially thinking back to how scaling the LLM improved things like text rendering?
Sure. They showed capabilities well beyond just replacing one object with another. For instance, really granular instruction-guided editing. Things like changing the font of some text in the image or the exact words written on a sign, maybe even applying a specific style, like turning the word crazy into wow, using a sort of fiery text effect. It also handles more advanced editing tasks, pretty well style transfer, in-painting where you fill in missing parts, out-painting to extend the image, even estimating depth maps. The model's ability to precisely manipulate text within an image after it's generated, that really highlights how deeply the LLM understands the visual input, thanks to those high-fidelity continuous features it gets.
Wow. Okay, so this paper really does seem to provide a comprehensive recipe. You've got the hybrid tokenizer solving that foundational conflict, which then enables a simple, scalable, autoregressive backbone that works smoothly with a separate high-res diffusion decoder.
Yeah, I think it's a landmark paper precisely because it validates this design philosophy.
Yeah.
Unification doesn't have to mean compromise anymore. By aligning those feature spaces right at the source, using that shared encoder, the Manzano team demonstrated really minimal task interference, even when they pushed the model all the way up to the 30 billion parameter scale.
And given that finding, you mentioned that scaling the LLM unlocked these emergent sort of world knowledge-informed generation capabilities, which the WISE benchmark picked up on, but the older standard generation metrics like Genevol and DPG kind of missed. That raises a huge point for the whole research community, doesn't it?
It absolutely does. That observation strongly suggests that our current state-of-the-art MLLMs might already be outpacing our standard evaluation tools, at least in terms of measuring generation quality and complexity. So if scaling unlocks these sophisticated capabilities that our existing metrics just aren't designed to capture, it really begs the question: how quickly do we, as a field, need to pivot and develop new, perhaps much higher complexity evaluation benchmarks to truly assess the full breadth of what these next-generation unified MLLMs can do?
A truly provocative thought there for you to mull over in your own work, especially as you build and test these kinds of next-gen models. Thanks so much for diving deep into the Manzano architecture with us today.
My pleasure. Always fun to talk about this stuff.